Hey, Carrie, how are you?
Good. How are you?
Good. I got to get myself organized and then I'll turn on my camera.
No worries.
There we go. Hi, guys. How's it going?
Hello.
Hey,
Hi.
wait another couple minutes. Hey, Sam. How are you doing?
I'm good. I'm okay.
Good.
How are you?
Good. Such a rainy day. It's like hard to be upbeat.
I know I'm very sleepy.
Yeah.
Oh,
Hi
hello
there.
there.
How are you?
Pretty good. How's everyone?
Good.
Glad to hear it.
Figure we'll wait like one more minute, guys, and then I'll just get going. And if people hop in, they can hop in. Perfect. And I'm gonna have my screen up too, so we have something to look at. All right, I think I'm gonna get going. So we have a bunch of prism stuff to go over. I think this stuff is kind of fun. Um, it's just it gets a little like you have to like it's easy to make mistakes. So I find that I like to kind of draw this stuff out. Um, but I do, like I said, think it's kind of entertaining. But the things that relate to what we're going to talk about first are the finally finishing book two, basic optical principles, and then the PDF called Prism Pages. So let me pull up that as well. But let's kind of start with um, looking a little bit at, let me pull up book two here, scroll through. Okay, so we did a good amount of stuff with focal length. Oh, I wanted to do that focal length example too. We'll have to come back to that because I know there was a ticket about a patient that wanted like a very specific focal distance. So we should just kind of circle back to that before we finish up tonight because that was a cool, very applicable way to use the focal distance stuff that we've been talking about. Sometimes I feel like this stuff is really theoretical, and so it's really nice to have examples of like, okay, this is how it would actually be done. So anyway, we looked at these pictures. Were kind of excuse me, some of the first things that were mentioned. Remember that when they're drawing out lenses here, they're showing the minus lenses first, and then they go into the plus lenses. If you can kind of see, excuse me, where my mouse is here, I'm kind of circling over the A picture here. This can be a little bit confusing how they kind of draw this out, but it's really critical that you kind of understand what this X is that goes through the lenses. Basically, if you kind of imagine the lenses as prisms, it's showing them almost as four prisms, really. So minus lenses are going to have their apexes, right? Their points toward the center, whereas plus lenses are going to have their bases toward the center. Okay, so we have it kind of going horizontally, and then we have it kind of going vertically for the plus lenses. So depends on what the direction of the prism is, but that's really important that you kind of identify this as prisms because that's going to be critical for figuring out which direction the prism is induced in, which is basically what a lot of this is all about. So I did want to, let me just pull up, let's see, we have for meeting 4, I also wanted to pull up this too. This was the first part of this document was just kind of a quick review. Remember that when light enters prisms, it goes towards the base of the prism, right? So you can see when it's a converging lens, it's entering in and then going down. When it's a diverging lens, meaning a minus lens, it's entering and then basically splaying out or spreading out. Okay. But basically, yeah, we'll kind of come back to this one. I thought there was a good picture here. Yeah, okay, sorry. I actually like the pictures on the other one better. So let me go. Pull that one up one more time. Quickly go to the bottom here. Okay. Perfect. So one thing that was important about the readings here. I believe this was actually in the Prism pages reading, but one of the things that I want you to remember, and definitely something that is on the test, is that they talk briefly about with motion and against motion. And I don't know if this is something that you guys have encountered before, but that was one of the first things that was discussed in the Prism Pages PDF. And one of the tricks that I wish someone had told me with this is that if you forget whether which direction the with motion is and which direction the against motion is, you can actually just pick up your glasses. I know most of you guys have glasses, or if you are going to take the ABO test, it's a good idea to bring a pair of glasses just because it's helpful for instances like this. But depending on whether you have a plus or a minus prescription, if you forget on the test, if they say, oh, our minus lens is with motion or against motion, you can actually just pick up your glasses. And if you're at home right now with a pair of glasses, I would recommend that you try this. So what with motion and against motion means is that if you have a pair of minus glasses like I do, what you would do is look at something straight ahead of you, like a line on your computer, could be like the side of your monitor or laptop, or whatever setup you have, or like the line of a doorway or something. But if you have minus glasses and you move your glasses back and forth horizontally, what you'll notice, I would close one eye to do this, what you'll notice is that the line that you're looking at will move with the lenses. Okay, so that's considered with motion. So minus lenses, it's going to go basically with the lenses. Now, if you have a plus prescription, you're going to notice that it's actually, that line is going to go in the opposite direction. So if you're moving your glasses horizontally, you're going to notice that the line that you're looking at is actually moving in the opposite direction. So that's all that they mean with motion and against motion. And so you can just memorize it, like with is plus, I'm sorry, with is minus and against is plus. But it is a nice little trick just to kind of have your glasses there and you can just kind of quickly test. That's kind of an easy, question right off the bat, or easy way to kind of get the question right without having to really remember it. But that definitely is something that was mentioned, and something that you should know. The other thing that they mentioned was that plus is going to be always magnifying and minus is always going to be minifying. So I think that's fairly straightforward. But if you think about, like looking through like an eyeglass, you know what I mean? Like why can I not think of the word? Like one of those big what's wrong with me? What's the word for those? Like
Magnifying
magnifying glass. I'm like an eyeglass. No, a magnifying glass. Like if you're like a detective, think about that as like a plus lens is there. A plus lens, it's going to be magnifying. If you looked at them, their eye would be like massive, right? And then if you think about minus as minifying, right? So the other thing, we did just go over this, but they're definitely going to ask on the test, definitely super important critical core knowledge is knowing that when light is going through a plus lens, it's going to converge. And when it's going through a minus lens, it's going to diverge. Okay, so things that were mentioned that you should definitely remember. They moved on to the prescriber's method, which basically is what we typically see. It's kind of the technical name for how we generally see Prism written. So maybe I'll do a quick whiteboard for that. I think I have to stop my share in order to do that. So let me do that real quick. But pull this up. But the thing that you will see on Prism, and hopefully you guys have had some experience with seeing a Prism RX, but basically, typically what you'll see is you'll see BO, you'll see BI, you'll see BU, and you'll see BD. Okay, so typically that will be written on the prescription. So that is very simply base out, base in, base up, and base down. Okay. And all of these super important, but all of these relate to basically where your nose is, or I should say primarily the base out and the base in relate to where your nose is, the base up and the base down. Pretty straightforward. It's just basically whether the base is going up or the base is going down, right? But if we're thinking about base out, you definitely want to be thinking of, let's try drawing someone's nose here. Gotta have nostrils if you're gonna have a nose, right? But basically, we're thinking about where that base is going in terms of their nose. Okay, so if it's base out, the base is gonna be going like that. If it's base in, it's going to be going like that. Okay, so those ones very critical that you're thinking nasally, that you're thinking about basically the center of the face. Okay. The Prism Pages book also mentioned something called the 360-degree prism method, which is basically just, saying, 90 degrees, 180 degrees, kind of 0 degrees. And it's basically the same thing. It's just kind of a different way to list out the direction of the prism base. Maybe that makes more sense, I would say. Like it kind of like it's difficult to kind of get confused about where the base is going. If you're saying, okay, it's at 90 degrees, like there's not a ton of debate for, kind of where that would be. But at the same time, it's not your typical measurement. You're more typically going to see base out, base in, base up, base down. So I would say don't worry about the 360-degree prism method that they mentioned in the PDF. Just know about this one that we're talking about now. Okay, so basically, the other thing that I wanted to remind everybody about is Prentice's rule. Okay, that was, I think, in very early on. Now I can't remember if it was the first class or the second class, but it was like one of the first things that I wanted to introduce everybody to, because I feel like that's something that is so common, such a big part of the test, and I just wanted people to kind of immediately get into it. So just to kind of write this down, make sure that you are very familiar with what the formula is. But basically, it means prism equals F, which is typically the diopter power. So I'm just gonna, oh goodness, that's supposed to be a D. Power. So prism equals F, which is the diopter power, times, I'm going to write des for decentration, but the really important part here is that you remember that this must be converted into millimeters. So all that stuff we did last class of like remembering how to put stuff into millimeters, centimeters or meters, and kind of going back and forth is going to come in a little bit here too. And then you're going to divide that whole thing by 10. Okay, so that is going to be what the Prentice's rule formula is. Now, we worked with that a little bit in the first one, and we're going to work with that one today. But I do just want to make sure that you guys are feeling confident with what that formula is. And then the second part of that, which is what we're going to talk about in just a minute, is like, okay, what is the direction of the base? It's cool to know how much is something going to be decentered, how much prism is going to be induced, but it's not like the second part of that is like, okay, what is the direction of the prism? Is it base up, base down, base in, or base out? So that's kind of part 2 of Prentice's rule stuff. All right, so what I wanted to pull up next, I'm actually just going to quickly take a screenshot of it and then just put it on the whiteboard. I just have to grab it real quick. I think it's from this here. Okay, so this was also from the PDF. I'm just gonna save this and then put it in. I know there's a way to put in an image here. I did it like a billion times last time, but I just remind myself. Oh, is it down here? Oh, sorry guys, I can't remember how to put in a an image. Let's see. Sticky note, shape, not a shape. More tools. Oh my goodness. Okay. Ah, where is this? I suppose I could. No, it's not gonna let me paste. I could have sworn there was a way to put an image in. Sorry guys, I apologize. I don't know why. Comments, templates, no. Timer, board. That is so strange. Oh, did you guys just put something in? Let me see. How the heck did I do this so many times last time and now it's like not obvious how this is done? I could have sworn there was some way to add this. All participants. Huh. Let me just quickly try a new whiteboard, see if that allows me to. Probably not, to be honest, but just out of curiosity. Okay, well, it's a pain in the neck. All right, so whatever. I guess we'll just kind of not worry about that. It's nice to show little snippets, but anyway, there was part of the reading where they talked about a concept called canceling and compounding prism. Okay. So it's basically whether prism is going to um, kind of have a compounding or kind of additory effect, or whether it's basically going to wipe itself out. Okay. So they gave, and what I was kind of hoping to show you the little snip of, is they gave some examples. And the first one that they gave was base in and base out. So I wanted to kind of draw those out for you because I feel like, again, I feel like drawing stuff out is a very, very helpful way of like visualizing this and understanding it. And I would encourage you to do that. If you do end up taking the test, I would encourage you to kind of draw this stuff out. So what I would do is I would just kind of make a quick nose and then kind of draw it out yourself. And we can kind of decide if it's going to be compounding prism, meaning they're going to kind of multiply on each other, or canceling prism. Okay. So if you have a scenario with a base in and a base out prism. Okay. So let's draw the base in prism first. Okay, so obviously we would have this be going over the eye, but we're just drawing it over the nose at this point. And then you also have a base out. Okay, so the thought here is that this is going to be a canceling situation. Okay, because if you imagine the patient looking through this, right? Basically, the bases are going in the same direction. Okay. So in this case, that's going to move both eyes in the same direction, right? So remember that one good rule of thumb in your head to remember. I know we mentioned this in another class, but one good rule of thumb is to remember that you're trying to get the eyes to go or put the base in the direction where you want the eyes to go. Okay, so in this case, it's pretty clear that if you're looking at this, the eyes are both going to go to the left in this case. Okay, so in this case, it's a canceling prism situation. All right, now conversely, one of the examples that they gave was if we have a nose here, and then you have a situation where it is base in as well and base in. Okay. So in this case, if I'm just going to kind of switch colors here, we are thinking that in this case, we want the eyes to go in and in. Okay, so in this case, they're not going to cancel each other out. The eyes are going basically different directions. We're trying to get them to converge. Maybe the person is having a little bit of trouble, with reading or focusing or bringing images together up close. So in this case, we have two base-in prisms. They are compounding each other. Okay. So a couple more examples just to illustrate this that they gave. In the book, they had base up and base down. So in this case, it's a little bit less important that we draw out the nose here, but we'll go ahead and do that. I'm sorry, I shouldn't have said base up and base down. Base up and base up. Okay, so if someone was prescribed this prism, it would be canceling, because in this case, we're trying to get the eye or the vision to go up. Okay, so basically, long story short is that if you have the bases of the prism going in the same direction, whether it's up, down, side, side, those are going to be canceling each other out, right? Because if the person were kind of looking through that prism, sure, their vision would jump over, however many diopters, right? But if it was, split between the eyes evenly, they're not really going to notice that, right? Like they're both going in the same direction. Whereas, let's give one more example for compounding. If you had, whoops, meant to do that, not in red, but so say you had this sort of scenario where you have your nose and you have base out and base out, right? Then in this case, you are going to be moving the eyes kind of in a exo direction, right? So they're going to be kind of diverging a bit, right? So in that case, they're going to compound each other. They're not going in the same direction. So they're kind of additive, multiplying on each other. Okay. Couple other scenarios. So if you had both bases going down, then that's going to be canceling. The other thing that they gave was to have one base up and one base down. Those ones are obviously going to be compounding. Okay, so easy way to think about it is if they're going the same direction, bases same direction, it's going to be canceling. If they're going different directions, they're going to be compounding. Okay, so that comes into play a little bit, when glasses are made and stuff. It's not, never really okay to have prism that's in the glasses unintentionally, which is kind of what the whole point of Prentice's rule is. But it's going to be a heck of a lot less disruptive if the prism is done in both eyes in the same direction. It's not really something that the person is really going to notice, right? So if, say two lenses are both, decentered, vertically a little bit, they're not actually really going to it's something that cancels out, right? So it's not really going to be a major issue. But anyway, let's move on to how do you kind of figure out what direction the decentration is going. So again, we've gotten kind of past the canceling versus compounding, and we're now going to figure out what the effective prism is. So the best way to do this, again, is, I think, to draw it out. If you get really comfortable with it, I would say you don't have to really draw it out. But I find it very helpful, and when I did the test, I would just draw it out. But basically, I'm just going to draw some eyes. I'm going to put in my pupils there. I suppose we could add the nose too, so let's go ahead and put in a nose now. But basically, what we're going to do is, in this case, we're going to kind of use some colors to figure out exactly what the center line should be. Okay, so what I typically do is I usually do kind of like an orange color. I'm just going to make this a tiny bit thicker. And what I use that for is I kind of go down straight from the pupil. And that is where ideally we would want, looks like the person looks kind of scary actually. It looks like blood or something. But basically this is ideally where we would want the person to be perfectly lined up in the center of the lens. Okay, so we would want that, that center line directly, and it doesn't actually have to go down. It could go above as well, but I typically use orange, no color that it has to be, but I usually use orange for like the ideal place. Okay. And then what I like to do is choose a slightly different color. This is just to illustrate it. Maybe when you're actually doing it, you don't really need to do that. But what I usually do is, for when something is decentered nasally, I usually just kind of mark in kind of a green line. And then when something is decentered temporally, meaning towards the temples, I'm going to kind of put in just a blue line. And just kind of helps me remember the direction of where this prism is going. So just as a quick illustration of this, I'm going to make my line a tiny bit thinner here. I'm going to go back, maybe I'll do like a gray one. But basically, let's say that we wanted to draw a minus lens. So let's say that we're going to put in a minus lens to the patient's glasses. And so what I'm going to do, I probably should have made these lines go up above the pupil. Sorry about that. But basically what I'm going to do is I'm going to draw a minus lens. Remember that a minus lens is two lenses that touch apex to apex. And then what I'm going to do is I'm going to be like, okay, so say we had this minus lens, we could have, I could draw the top of it and the bottom of it too. But for these purposes, we're really just looking at horizontal prism, so base center out prism for these examples. Basically, what I could do in this case is I could say, all right, so it's decentered temporally, okay? What kind of prism is induced? So I'm going to look at where the orange line is, where the pupil is, and I'm going to figure out which prism it's in, okay? So this is a minus lens. Again, it has apex to apex. Bases are out, and I'm going to say, all right, so obviously this pupil is in this prism that's on the left here, and then I'm going to say, okay, what direction is that prism's base going? And in this case, we have, oh, here I go, trying to write, we have base in, okay, because it's base in, it's going nasally, it's kind of going toward the nose. So in this case, the prism that would be induced would be base in prism. Okay, if it were shifted to the other side and we were having the pupil kind of show up in this prism, it would be base out prism that was induced, right? So to show you quickly just another example, let's use a plus lens. So in this case, let's have it decentered out again. So I'm going to draw it over my blue line here. But we know with a plus lens, that means that the bases are together and the apexes are out. So I'm just going to go ahead and draw that like this. Like this. And basically here we can see, that it's decentered. I put it on the blue line because I wanted it to be decentered out. I'm going to check out what prism it's in, and I'm going to figure out what direction the base is going. In this case, the base right here is going away from the nose. So that is going to be BO or base out prism. Okay. So this is why I find that it is extremely helpful to draw this out, because otherwise I feel like it's very tricky to visualize. Again, if you work with it all the time, if you're doing this like just on a daily basis, like you wouldn't need to draw it out. But if you're just kind of like figuring this out here and there, I definitely find like I need to kind of visualize this to really get the base direction correct, because it does get confusing because we just did two examples of them being decentered temporally, but if we had done an example of them being decentered nasally, it would be the complete opposite. We would have gotten base in on this side and we would have gotten base out on this side. So again, in my opinion, really helps to draw it out. Let me just quickly close the whiteboard, and I just wanted to return to that picture that I had up before from the book. I think it was this page here. Okay, this is what I was trying to show you, this picture here of the canceling and compounding. But the one that I wanted to go back to was the ABO books. And then go way down here. I just think these pictures are really nice examples of how to kind of visualize, the direction that the prism is going to be going in. So you can see, here, like just in all of these pictures, you can see, oh, okay, this is an example of, so if you're looking at C, I don't know if you guys can see my mouse moving on the screen, but if you're looking at example C, with base in prism, basically you're looking for where the pupil, which prism is the pupil in, and in what direction is that base going, right? So in this case, in C, it's base in prism. In example D, you're looking for what prism the pupil is in. It's in the prism on the temporal side, so the prism is base out. You can also see in E and F, it gives you a nice example of what base up prism looks like in the example E, and what base down prism would look like in example F. And then very similarly, if we scroll down to the plus lenses with the base to base drawings, you can really see, what does it look like? Again, you're just looking at the pupil. You're trying to see, if you're looking at example C here, you're looking at the pupil, looking at the direction of the base. So that's going to be base out prism. The thing that gets confusing about it is like in example C, it's like it's base out prism. But I feel like in my head, I want to say that's like base in prism, because I'm like, wait, that prism is towards the nose. But in fact, it's not about where in the lens the prism is, it's about what direction the base is going, right? So in that case, to me, in my head, I'm like, oh, that's backwards, but it's base out because you're looking at the direction of the base. In D, it's base in prism. Because again, even though it's the prism that's on the outside, you're looking at the direction the base is going. And then I do feel like the base up and down, fairly straightforward. You can see that, in the right eye, in example E, that the prism is going base up. And then in example F, you have base down prism in the right eye. So I don't know, I feel like relatively straightforward, but definitely very helpful to just go over and draw. Let's do a quick example. So I feel like I keep kind of alternating between screen sharing and whiteboard, but I am going to kind of quickly go back to the whiteboard here and just kind of draw an example. So we had an example that actually don't recall where this example is from, but I got it from one of the readings. But the example was, and this is the thing that's like the super common stuff that you're gonna kind of see in the practice like, or in like a practice test, but also in like the actual test. So I wanted to go through a few of like, how do you apply this, right? So a pair of glasses has a prescription of -6 OU. Okay, so very simple prescription, just a simple -6. So as soon as you're seeing like minus, you want to be imagining what that lens is going to look like when you draw it. Okay, so when you draw it, you're going to be drawing it apex to apex. And you ordered a PD of 62. Unfortunately, you received PD of 58. Okay. So let's just quickly draw that out. We have -6 in both eyes. The PD that we wanted was 62, but instead the PD that we received is 58. Okay, so basically what we're going to do is we are going to first apply Prentice's rule. So in this case, we are going to go back to our formula and we're going to do the power times the decentration. Okay, so in this case, something we haven't quite talked about before, so let's go over this. I'm sure you guys saw it in the readings and everything, but let's figure out how much it is decentered, and you have to do it in each eye. Okay, first you figure out overall, and then you figure out in each eye. Now in this case, they're talking overall PD. They're giving you a binocular PD. They're not giving you like a separate PD for each eye. If they were, then you'd have to figure it out, individually by eye. But in this case, they're just like the overall PD is 62. In our offices, we don't typically take PDs like that, but in a lot of offices, they do not do monocular PDs. They're just like, hey, like we're going to take, the overall PD and use that, and then it'll be split between the eyes, right? But basically what we want to do is we wanted a 62, but we got a 58. Simple math tells us that there are 4, make a little arrow down here, 4 millimeters between that. Now we have to divide that by 2 for each of the eyes. So that means that it is 2 millimeters decentered in each eye. Okay, so we're going to figure out this per eye, but remember Prentice's rule, we have to multiply the power, right, times the decentration in millimeters. Okay, so we know that it's 2 millimeters. And then we have to divide the whole thing by 10. I'm going to just do this with my calculator so I don't make a mistake at this point. So 6 times 2 is 12 divided by 10. So that means that we are going to have induced 1.2 diopters of prism. Okay, so it's hard to see that little dot here, but it's 1.2 diopters of prism is going to be induced. Now what we do is we figure out, okay, well, we can also figure out, is it compounding or canceling? But first what we want to figure out is it going to be base in or base out? Okay. We know in this case that because we're doing a PD, it's going to be horizontal, right? We know that we wanted a wider PD and we got a narrower PD in actuality. So this is going to be, we're not dealing with base up or base down. In this case, we're dealing with base in or base out. So in this case, I would just do my quick eye drawing. I'm going to just do my pupils and pretend that irises don't exist here. I'm going to quickly put in my orange, not quite over the pupil here, my orange lines, and then I'm going to do my green because we are in this case going in. Okay, where the issue is that it came smaller than what we wanted it to. So then what I'm going to do is I'm going to go ahead, I'm going to draw my lenses, and because this is a -6, that means that we're going to be drawing minus lenses, not plus lenses. So I'm going to go ahead and over this green line, I'm going to go ahead and draw what the minus lenses looked like here. And then I'm going to figure out, okay, if I look, I guess this pupil is a little bit easier to see over here. I'm going to go ahead and be like, all right, which prism is this in? It's in the prism with the base going out. Which prism is this one in? Again, it's in the prism with the base going out because it's going away from one's nose. So in this case, switch my color back again. We would have 1.2 diopters of prism induced base, I'll just put that here, base out. That would be for just one eye. So if they were asking you also, what is it going to be canceling or compounding, or what is the total prism that is induced? It actually would then become 2.4 if you're kind of putting together, because obviously 1.2 times 2, or for both eyes, it would actually become 2.4 diopters of prism. And because the bases are going in opposite directions, right, that means that it's going to be compounding prism. Okay, so in this case, I'm just going to write comp. Now, if we had the bases, say, on this side, just hypothetically, the direction was going this way, the base, was going in the same direction as the other eye, we would actually have no prism induced because it would be canceling prism. But in this case, because both bases are out, they're well, I shouldn't say diverging, that gets confusing, but they're going in opposite directions. The eyes are not looking in the same direction. That means that it is compounding. And if you were to ask, between both eyes what the total power is, it would be 2.4 diopters. So that was a lot of steps to that question. Usually they're not asking you if it's also compounding. They're not usually asking you the total prism power, but it's very common for them to be asking you what direction is the base going. So let me just take another minute to go through a couple more examples of that. We have a good amount of stuff to talk about. I'm like, oh my goodness here. So I don't want to spend too long on it, but I do want to I feel like it would be helpful to just go over a couple more. One other thing that I wanted to mention that was mentioned in the reading is talking about splitting prism. You guys probably, if you are teching a lot, you probably see the doctors do this frequently. Like most often, like if someone has like 8 diopters of prism, they're going to split it between the eyes. And this is generally really just like a cosmetic thing because, it would be weird kind of to just have like one lens that's like, say it's like base out prism of like 8 diopters. That's going to be like a really, really thick lens that, you wouldn't want to just have the one eye have this massive lens on one side and have the other eye be like nothing. So typically what they'll do is they'll just split it, and it would be like split between the eyes. One thing, I don't want to go too quickly on that, but one of the things that they did go over is, say you had an example where the patient needed 8 diopters of base in prism. What you would do is, if you needed to convert that to be able to be like, okay, let's split this between the eyes. Like, say this is actually something an optician can do. Say the doctor, prescribed the prism. Then like you're making the glasses and you're like, well, why would I just put this in one eye? It's not going to look very good. So what you would do is you can actually split the prism between the eyes, right? And so in one eye, you would have 4 base out. But going back to that concept of compounding prism, you still need 8 diopters of total prism. It's got to kind of, add up together again, right? We don't want it to cancel it. If I made both of these base out, all of a sudden we would have messed up because we had no prism. So that means that you have to change the direction to basically to the opposite direction. You don't want to suddenly go up or down, but if you have base out, you're going to then switch the other side to base in, because you still want the effective 8 diopters. So again, you're just adding these 4, but you're splitting it nicely between the eyes, and that will make it compounding prism. So that was mentioned in the book. Definitely a good thing to know about splitting prism. Same thing would apply if you had base up prism. You could split that. Say we, rather than 8 diopters of base out, we had base up. It would be 4 base up and 4 base down would be what you would split it between the eyes to be. So I should have saved the lenses, but the other day we had a patient that had a lot of prism. She had 9 diopters of prism in both eyes, and her lenses were just this really one thing that's really good to know as an optician, and it's hard to kind of know what this would look like without seeing it. So I wanted to kind of tell you. I mean, her lenses were like, if you ever wanted to like see this illustrated of someone's of what prism looks like in a lens, like it literally looked just like a prism. Like it was super thick. It was 9 diopters. Like I said, it was super thick, in her case, on the temporal side. But it was just really interesting. So if you are working in optical, definitely super important to recommend a higher index in these cases. Prism over 4 diopters is something that's really going to thicken the lens quite a bit. So definitely significant, and it's going to cause a lot of, anytime you get a thick material, it's going to cause a lot of distortion in the periphery. So any kind of improvement in the optical quality. Remember, we talked last week about ABO values. Rather than just kind of going ahead and doing that in poly, would make a ton of sense to move to a material with a better ABO value, which generally is going to be a high index material, because it'll also reduce the thickness there too. So just a kind of a real life example of that. Let's just quickly go over a couple, or maybe 1 or 2. Again, I don't want to spend too long on this, but let's just quickly go over a couple examples, and I'll just try to draw them out super quickly. So simple practice question would be, a minus lens moved downward from the primary position would result in, so let's just say very kind of rudimentary drawing. Here we are. In this case, we haven't done a lot of up and down, so let's just go ahead, and this would be the ideal place for the lens to be, right over the pupil. But in this case, we said a minus lens moved downward. Okay, so in this case, we're going to start our minus lens apex down. It should be on this yellow line, but in this case, it's not. Okay, probably don't need to do the other eye here, but I'll just do it real quick. But basically, in this case, now you're looking for where the pupil is, right? So the the question would be, if a minus lens is moved downward from the primary position, take a look at where the pupil is and check out where the base is. So in this case, we are going to have base up prism induced in this case. Okay, so simple, simple question. They're not asking you to actually calculate this out. Let's do one where we do have to quickly calculate it. I would be screenshotting these and putting these up, because I definitely love to see the actual question written out, but because I can't seem to put in any images. Let's say we have a +2 diopter lens, decentered 5 millimeters beyond the patient's measured PD. So in this case, we're just going to, beyond the patient's measured PD is a bit ambiguous, because it's like, all right, is this the total PD or is this for one eye? But in this case, I'm going to assume that this is just happening in one eye. So basically what we're going to do is we're going to do our apprentice's rule. So it's going to be, very simply, 2 times 5 divided by 2 times 5 is 10, of course, divided by 10. So we get very simply a 1 diopter answer. And then we have to figure out, okay, what is the base direction going to be? So we have our eyes here. We'll draw in our lens. We said that it was decentered beyond the patient's measured PD. So we would assume that that's going to be going out. So we would put our bases here because the center of the lens is now out, like it's bigger than the patient's actual PD here. So in this case, we look at where the pupil is, we figure out what the direction of the base is. In this case, it's going to be base out in these. So in this case, we have the answer would be the 1 diopter base out. Okay, so, just quick drawing, it's just kind of sketching it out, definitely helpful in these cases. So I did have a couple others that I could go through. I feel like we've talked a lot about this. Maybe I'll save those for another class that will obviously, kind of will return to this. But I think I've kind of exhausted the topic a good bit. But again, we can certainly go through more. So if you want to let me know, in the channel or something, you could certainly tell me if you feel like you're confused a little bit about it at this point. So, but that's a good one to practice and to feel confident on, because I feel like that comes up like you'll have at least like 5 questions out of the 125 questions like about this, if not more. I felt like when I took the test, I kept having stuff like about this. It just seemed like a really big part of stuff. So, all right, so I did want to also talk briefly about the lens curves that we talked about, or that we read about in the book as well. So they did go over different lens forms, and I'm just gonna go through my the things I gave you to read just to find the images that are helpful here. So I'm going to get out of this whiteboard briefly and then go back to sharing. This one. Okay. Okie dokie. So with the lens curves, okay, this is another like really critical thing. There's a lot of like really important stuff in this other kind of in the other chapters, like the lens discussions and lens form stuff and the curves. But basically, you want to be very familiar with these shapes of lenses, which are shown here. So we have biconcave. Think about, whether something is sunken down and that's concave. Think about if something is convex. Think about that as like a little hill. We don't typically see biconcave lenses, but I do have kind of a neat picture of some lenses that I did want to show you before we move on to anything else, because sometimes they will do biconcave lenses when someone has a super, super high minus script. And then one thing that we might very well see is a pair of glasses with plano, like no curve basically on the front, and then a concave curve on the back. This one is plano convex. I would say that would not be something we would typically see. And then the thing that we see all the time is meniscus lenses, right? So those are going to be, depending basically on their prescription. This one is going to be much more like a plus lens. And this one is going to be something you would typically see for like a minus prescription lens. So definitely want to be familiar with these shapes and how to describe them. I would say the plano ones are kind of, the ones that you're unlikely to be asked about, but it is kind of nice to know about them. Okay, so they did talk a little bit about curves. and about radius. And I did want to, here I go. Now I'm gonna switch back again to the whiteboard. I did want to touch on the curve thing just briefly, because I know that this is something that comes up in contacts, and it's definitely something for the NCLE exam that they talk about like a ton. So I just figured we would kind of briefly go over that. But basically, what they were saying about um, rate, hold on, about radius is okay. So if you have a large sphere, and the real key here is imagining cutting off part of that sphere, right? So like when I see this, like this shape kind of here at the top, I always think of like a contact lens, right? Because this is, kind of, if it's aspheric, maybe not as much, but if it's, if it your typical contact lens, then it's going to be like think of like a big beach ball and they just like sliced off part of that beach ball, right? It's going to be a little piece of a sphere like this, okay? The idea being that if they hadn't sliced that off, that little part, that little contact would go on to make an entire ball, basically. It would become a sphere. And that's an important concept. One other thing that you want to think about here, and I'll draw another quick circle. Ugh, that is a bad circle. I'm not going to go with that one. Well, it's going to have to stay because of my lack of whiteboard skills. Actually, no. Sorry, guys. Let me do a really little sphere. Okay. So let's think about cutting off this. Okay. My drawings are not ideal here. But what I wanted to point out was that if you have like a larger ball, a larger sphere, right? You are going to have in this area, oh my goodness, this curve, if I can draw this, okay, is going to be flatter, okay? Then, and again, this is not a really ideal drawing, but hopefully you can kind of tell. This curve here in green that I drew is much flatter, right? Like it's kind of like a nice little slope like this, than the slope that's in a smaller ball, right? So this one is much more kind of along these lines, whereas the other one is along those lines. So it's much flatter, okay? So larger sphere, flatter curve. The other thing that you want to know about this, just in general, is that if you had the radius, okay, so think about half of this, right? On a larger sphere, it's going to be, think about this orange line, it's going to be much longer than the radius of a small sphere. Okay, so that's quite obvious, at least, that this, if it's a small sphere, you're going to have a very short radius. If it's a larger sphere, you're going to have a longer radius. Okay, larger curves, so flatter curves, are going to have less power to them, and steeper curves are going to have more power to them. Okay, so if next time you're looking at somebody's glasses, say you have a pair of glasses that you're noticing that the optician is working with a patient with, or if you are the optician and you're working with a patient, and take special attention to plus lenses, okay? What you'll notice is the higher the plus power, now this isn't always the case, but in most cases it is, the higher the plus power, if you were to hold those glasses and kind of look, I'm trying to hold them in the screen here, if you were to kind of look down on them and kind of like be like, all right, like what's the shape of this lens? Is it kind of popping forward, or is it flat? Is it, convex, concave? You'll notice that the higher the minus script, the more they're going to be convex. Okay. So it's going to have much more magnifying power when they're kind of steeper, and so you'll really see that be the case in the plus lenses. I feel like that's a good example of that. So anyway, larger sphere is going to be shallower, going to have a longer radius, going to have a flatter curve, less power. Smaller sphere is going to have a short radius, more power, and a steeper curve. Okay, so just good, good kind of things to remember there. All right. So other things that we need to absolutely be confident with. So we have the nominal lens formula, okay? So that says that the front curve, so front, I'll try to abbreviate this, curve, plus the back curve, oof, goodness, curve equals the total power. These are kind of fun as well. So front curve plus back curve equals the total power of the lens, okay? So this is kind of, you know, it's a little different from the optical cross stuff that we looked at last time. So I know that can be a bit confusing here. But what they're talking about is they're talking about if you used a lens clock, and I did ask you to watch a quick video of a lens clock, just so you had a good sense. I know in the Northborough office we do have a lens clock, but I honestly am not sure, if this is something that you would find in like Worcester or Holden. Well, maybe Holden, but basically, they're not something that typically you're going to use on an everyday basis because you're just going to read the lab slip and figure out what the power is. You're going to put the glasses in the lensometer and figure out what the power is. You don't usually need to, kind of do this the old-fashioned way, but it is a good thing to know, obviously, and it's definitely on the test. But basically what they're saying is if you use a lens clock to determine the front surface, you put that little lens clock on the front surface of the lens, and then you flip it over and you then do the same thing on the back surface of the lens, you can, using simple math, determine what the actual power of the eyeglass lens is. Okay, so let's take a look and we'll look at two optical cross examples. So say we looked at one side and we found that, and this is a spherical example here, we found that in the points of the lens, now this would be the same for these points as well, but typically we just label the two, it's going to be +4. Okay, so then what you would do, we do our little plus sign. We check out the other side of the lens, and we find that in that case, it's reading at -2 across the entire lens, okay? So that would mean that with simple math, we could figure out that the power of that lens is going to be +2 diopter sphere, okay? So, pretty straightforward in this case. We're really just using, you know, positive and negative numbers, simple math to figure out what the power of the lens is, whether they're in a pair of glasses or not. But basically, you're using the lens clock to figure out the curves and then figuring out the prescription, which is pretty cool when you think about it, right? Because it's really just, different spheres and curves, and it kind of like goes back to very like kind of basic opticianry concepts where you would be actually like grinding out a lens and you'd be like, okay, well, we need to get to this power, so I'm going to put one, I'm going to grind it to this power here, and then I'm going to grind it to this power here, and then mathematically we'll get to the correct power of the lens. So fairly straightforward with spherical lenses. I did want to go ahead and show you what the optical cross would be like for a toric lens, right? So for a lens with astigmatism. So let's use this example here. We are going to say that the front of this lens, we're going to kind of keep our +4. Now, one thing just for practicality to kind of remember is that it would be very unusual for a eyeglass lens to have any kind of toric power on the front. It's going to be, the same curves always on the front of a lens today. That probably was different in the past, but now you would only be getting a spherical curve, just one curve, I should say, on the front of a lens. And then if you were to look at the back of the lens, let's say that you found that there were two curves, okay? So in one direction, we had a curve of -6, and then in the other direction, we had a curve of -5, right? So that should tell you that, there's probably going to be some, well, there is going to be some astigmatism here because these are not, as in this example, these were the same power across the entire lens. But in this example, we have a -5 running across this way in the lens and a -6 running across this way in the lens, okay? So if we were to put those ones together, we would come out with a -2 and a -1. Okay. So again, we haven't changed the signs. We've just kind of combined positive and negative numbers. So that would mean that in that particular lens, we have a -2 and a -1. Those are, what the power basically is in the lens in this case. Okay, so let me just take a second to read through my notes here. Want to make sure that we get everything in here. Okay. So I want to go a step further. You know what? I don't feel like I don't have quite enough time to finish this part. So you know what I'm going to do? I'm going to return because I feel like this is an important concept. Like we should probably leave it at this for today. And what I'm going to do is in our next class, I'm going to kind of finish what I wanted to go over with like the next step of this. Because here, okay, we can kind of figure out what the powers of the lens are in this case, but I want to bring it a step further with you guys and kind of explain how we could write this into an actual prescription and what that would look like. But let's kind of leave it at this for right now because we're getting a little bit short on time, and I did want to just spend a couple minutes looking at the frame information that I asked you guys to kind of go over and read too. And so what we'll do is at the next meeting, we're going to go back to the optical cross and kind of tie back in because we did do stuff with the optical cross, and it's like this is kind of this all relates to the optical cross, but I want to show you how that all ties together. And I feel like it's going to take a little longer than what we have. Let me quickly show you. I had some cool examples that I wanted to show you of just a couple pictures of glasses that I think would be neat. So just to kind of illustrate a couple of these concepts, I'm just going to share my screen one more time. Okay, so hopefully you guys can see this okay. But basically, maybe I'll zoom in a touch and see. Doesn't really do too much. But anyway, this particular pair of glasses, it looks like it might be a kid's pair of glasses. But this is kind of cool. This is basically biconvex, right? This is the front of the lens you can see is convex as well as the back of the lens, right? What makes it a little harder to see that is they've actually basically taken off the edges of the lens. Like if I had like a pencil here, I could just kind of draw out where the point of this lens would have been, but it probably would have messed with the edge of the frame. It would have been sharp. So basically, they've literally just sliced off the point of the lens, both here, which it would have been kind of like out like this, and then out like this down below. I don't know if you can see my pointer, hopefully. But basically, they've kind of trimmed it off. But I thought that was really cool. This is a minus 32, which obviously is an insanely high prescription. Not something you would see every day. But they needed, in order to get this power, they decided to surface it. There's a few ways to do this, but one of them is, I don't think we read about this yet, but a lenticular lens where you have like a little, um, like you have the prescription in like a circle in the middle of the glasses, and then around that circle is like nothing. It's just kind of like a carrier for the prescription. So that's one way you might do a really high script, but in this case they just made the script, both on the front of the lens and on the back of the lens. So I thought that was kind of a cool example, of a super high powered lens. And then I also wanted to show you, this picture here, of this super high wrap lens, frame, because one of the things that you bump into a lot, as an optician, especially if we used to sell Oakley sunglasses, and this would come up like all the time, and it's one of the reasons that we, stopped selling them. But this does happen with some of the Maui gyms that we sell that are like really highly wrapped. But basically, you really can't do this in a high minus prescription, right? So if you think about this, like the frame itself, right, is so wrapped. There's so much face form here that if you try to imagine, putting like a minus lens in here, remember that the minus lenses are going to have, thick, edges temporally. But basically, like you would have the lens kind of coming out in like a point, like way back here, right? It would be super thick back here if you had, a high minus, lens. So that's going to obviously start to like interfere with the patient, because it's going to start to like, it could potentially like bump into their cheek because it's sticking out so much. I mean, you can kind of roll a lens and like trim it down and stuff, but it really can only go so high. And one of the reasons for that was talked about a little bit in these chapters is that to fit into a sport frame, you would have to have, a very high front curve. You'd have to have like typically what would be used for a sports frame is like a base 8 lens, right? So if you have like a kind of a +8 on the front, you really want to think about, wow, like say you had like, let's say like a, I don't know, say your script was like a -8, right? So you automatically have this front curve of like a +8 to get it to fit in the frame. Because if you did like a flat lens, like say you did like a base curve of the lens of, say, like maybe like a 2 or something, right? It would be like really flat. It would kind of like come out like this, and it wouldn't like fit well into the shape of this lens. I mean, the shape of this frame, because the frame itself kind of has like a base curve, for lack of a better term. So you would typically, in a wrap frame like this, you do like a base 8 lens. So that's like a +8. And then say the person was like a -8, you would have to do like a -16 curve, right? At minimum, to on the back to get that correct power, right? Because you have to get rid of all that +8 in the front, then you'd get to plano, and then you have to get to the -8 still, right? So that would be like a 16 diopter curve that would be needed for the back. And that's going to be so like curled out, and like the edge of it is gonna like come out so much, that it's just gonna look ugly. It's like you'd end up having to kind of stick some of it out the front. The patient's gonna be unhappy. There's gonna be like tons of distortion because it's like so thick on the side. So I thought that was a really nice like real life example of like, why can you not do a high minus in a high wrap frame? And hopefully that illustrates a little bit of the concepts, that were talked about in these chapters, like, thinking about like the front curve of a lens and what that would do to the prescription. So just to kind of reiterate that, like if you had to do a front curve of the lens of like a +8, but you're doing like a -RX, like you have to still get to that -RX, using the front surface and the back surface of the lens. So that puts a lot of pressure on the back surface of the lens to be extremely, curved, and to have like really dramatic curves, which just isn't going to be nice optically, and isn't going to, isn't going to be a good situation. So a lot of times it'll be like the highest they'll do on these is like a -4, maybe just like a -3, and then of course astigmatism comes into it too. So I figured I would show you that. But last thing that I wanted to go over, because we are getting a little bit short on time, let me just go over the frame materials. Um, I feel like we spend a lot of time on the math stuff, and then sometimes I'm shortchanging a little bit of some of the more fun optical related things. But I want to make sure that you guys feel really confident in the math stuff because typically that's the stuff that people find a lot harder. To be perfectly honest, a lot of the optical kind of frame related things, some of the lens things, but a lot of that stuff is memorization and just kind of committing to memory. In this case, you want to know what optial is. You want to know, I think, like, knowing nickel is, you know what I mean? Like you want to kind of know what typical frame materials are. You want to be able to know what their properties are. Um, and it's honestly it's fun to talk about, but you have to memorize it is really kind of the long and the short of it. So let's go through a little bit about this. I thought this was kind of a neat chart where they're kind of telling you right away what the typical materials are, what's plastic, what's the metal, and what are the other materials. I don't know if you guys have seen the only carbon fiber or stuff that we really have in the offices that would fall into the other categories. Sometimes we will have some carbon fiber Oakleys. We used to have, I think, a couple of Ray-Bans that had carbon fiber temples too. I don't know if we still have any of those around, but carbon fiber obviously super light. You know it from cars, probably motorcycles. And then I don't think we've had any sort of Kevlar related things for in our offices. We have some rubber coated things, which are a real pain in the neck to work with because they tend to be very easy to damage. We've had some sagas with rubber coated Ray-Bans lately. And then in terms of natural materials, that's a really fun area to discuss. I would say, if Fallon were here, she could probably tell you a little bit about working with like buffalo horn. That's kind of a high end optical material that is notoriously difficult to work with. I have to be honest with you, I've never worked with frames that were made out of horn, but I hear that you have to be extremely careful with them. They're extremely brittle, and you have to know, when to apply heat and when that makes sense and when that doesn't make sense. So it's a very kind of fancy, expensive material that frames used to be made of a lot more, but nowadays it's really only extremely high-end frames that would be falling in that category. I would say like there's a lot of like really cool like niche stuff where people will make frames out of like just I don't know, they'll just go to like all sorts of like cool lengths. It becomes like, more like art or sculpture in some cases. With certain companies, there'll be like wood frames. I remember when Chris and I went to Mito, which is a show in Italy, where they tend to have like a lot of, I don't know, maybe it's something about Europe or something, but they have like a lot of these vendors that are very like small. It'll be like a one person company and they're just like this kind of crazy person that's like really into making frames with feathers on them. Or there was one company that we talked to that they would make their frames out of like stone. They were like which sounds insane, but it was like these very thin, almost like if you guys have seen like slate, it was like these super thin pieces of stone that they had like sliced to be like just a couple millimeters thick, and then they had like applied it to another material, and so the frames actually had like a stone like face to them, which was really cool. So there's lots of like really neat stuff like that. You know, if you were ever to work in, you know, a niche, very like high-end optical, certainly, you know, that's a place that might carry something like that. Definitely very cool. Definitely, I have to say, freaks me out a ton because, yeah, just the chance of damaging something, or, you know, the expense of the frames, and the potential for people being really mad at you because you didn't know how to handle it, or it just was a inherently weak material. Those are definitely things that make me nervous, but super, super neat stuff. And there's a little bit of this stuff, I would say, at Vision Expo. So in New York City, Vision Expo's kind of a fun show to go to. I feel like I know Carrie has been, I believe, to it. But you know, if we, you know, if you ever wanted to go down, or if we ever did like an office trip, there might be there's a little bit of that stuff there. Less so than what we saw at Mito, but that's a good place to see some of the kind of fancier materials and get to kind of touch them and stuff. I thought the parts about the xyl frames, the cellulose ones, were really interesting. You know, if you if you read through, there's some crazy stuff. Like the cellulose nitrate being illegal because of its flammability. That's kind of an interesting thought. Like, okay, it's flammable, all right. So, like, does that mean like when someone's smoking, when someone's cooking, like how does this come about? But you know, things that you'd want to you know, have in your head about this is you know, really just kind of like, when was it an early material or is it a current material, right? So cellulose acetate, that's, you know, one of the earlier ones. Um, the cellulose nitrate, another one that's going to be one of the earlier ones. Cellulose propionate, another, you know, kind of older one. Um, Nylon, that's definitely something. Sometimes you'll see frames that are injected into a mold. This is an interesting thing to kind of know about as well. When a frame is made, it's typically made from an actual sheet of acetate, right? So when we have our frames made, so when we have our new line coming, it's coming up. It's shipping on October 7th, which I'm really excited about. But we're like, so when we order frames, or for when the B Frank frames are made, they're actually like sheets of acetate. They're like these massive, well, not too massive, but they're like these table-sized sheets of acetate, and you can get them in either 4 millimeters thick or 6 millimeters thick, and they actually, you know, they actually saw out with a machine. They saw out the front of the frame, right, from like a sheet, like a rectangular sheet of plastic, and then the machine cuts out, you know, the places for, you know, where the eye holes are, and then a different machine cuts out the shape of the temples. So, you know, that's one thing that's important to know, is that most, you know, acetate frames are made from sheets, and then if they do end up having face form, they're just heated to kind of mold to the shape of the face. They're polished. Now, one thing to know is that nylon frames, or I believe TR90 frames too, are injected. So the ones that are in our office that you might see that are injected, I know Oakley does a lot of injected ones. We do have some Oakleys that you could probably see, or sometimes it'll even say on the frame that it's injected. But basically, it means that, you know, it's the material is melted and then put into a mold rather than actually cut from like a sheet of acetate. So those are, you know, more flexible. They tend to be lightweight, so those are the advantages of those. One thing I would say to you guys is, when you're in the office, like, pick up a few different xyl frames. Um, if you pick up like a lowercase frame, they use like and we have those in Northborough. They use a very like chunky, like, quality acetate for their frame. So if you pick up like I'm sorry, like, did I say Northwest? I meant to say lowercase. I don't know if I said lowercase or what, but I meant to say, I don't know what I said, but it should have been lowercase. But pick up a lowercase frame, and try it on, like kind of get a sense for like the feeling of that acetate. Um, because my guess is that that sort of acetate is probably a little bit more similar in feel to kind of early cellulose acetate. Whereas if you were to kind of pick up, a Tiffany frame, a LaFont frame, still super nice acetate, but it feels very different. And you'll notice that they tend to be more bendy. They tend to be affected more by heat. And my guess is it's just kind of the different, you know, polymers and different, slightly different ingredients and ratios that they use, in them. But it's just, when you're there, I would say, take a little look around and see some of the different feels. Obviously, you're not going to be seeing any of these older types of acetates, at this point. One other one I wanted to go over was Opteal. That is definitely one. The brand that uses this is Gucci, and to identify it, you will want to look at the temple. Like, so it'll say Opteal, inside the temple. And this one can be, very easy to break, and it can be a pain in the neck, because you have to heat it, quite a lot to get it to be adjustable. But once you get it to a point where it's heated appropriately and to be pretty hot, like more than you think you should, it's extremely easy to bend, and to adjust. But if you try to, adjust it, without heating it, it's like it snaps. It just kind of, breaks right off. So if you ever are working with Gucci frames, be very careful. Or, if you were ever to work with, frames that you weren't sure kind of what the material was, definitely take a look at the temples and see if it says Opteal, because it is very easy to break, and you do need to use quite a bit of heat. Sometimes it's going to be so hot that you don't want to touch it. So sometimes wrapping it in like a cleaning cloth, is something that will really help you out, with something, like Opteal, where you have to get it really hot. On the converse side of that, you do not want to heat. Like, we tend to be very like cautious, with everyone in optical being like, don't heat it too much, like you'll melt it. Because most of the acetates you will just melt, especially if it's a high quality one, like LAI works, they're like super easy to melt. I find, like LaFont is easy to melt, so you gotta, be very, very cautious, if you're, especially, and when I'm talking about melting, I'm not typically talking about like a temple. It's more about like the eye wire area. Sometimes you can melt it and you'll mess the bevel up, and then, one, it'll look bad, and two, it'll be really hard to get the lens into it. So you just want to be, in general, you want to be extremely cautious with heat, except in the case of Opteal. So those are good things to know. Metal frames, I mean, in general, the ones that, we're working with 9 times out of 10 are going to be stainless steel, right? They tend to be, fairly light. They tend to be flexible. They tend to, not corrode. They just tend to, last a long time. It's just a good solid material that can do a lot of different stuff. Um, Nickel silver, I would say, that's something that's kind of more on the old fashioned side of things. Things that you would want to, know about it. Um, that it's not that it's something that can corrode, right? So, if you sometimes have a patient come in, sometimes people are allergic to nickel. So you'll see them get like red spots, like anywhere, like where the frame touches, because even stainless steel has a little bit of nickel in it. But it's definitely something that, how like sometimes you'll see metal frames that are green. That's the nickel, that is reacting. So it's kind of, sometimes not the most ideal material, for frames, um, as well. Monel, I don't know that we have any frames, that are made, of this material. Um, sounds to be perfectly honest, like sounds like it's more, more something that would have been used a little bit more in the past, maybe something that a higher end brand would, at this point use. Does seem to be quite a large percentage of nickel. So probably, a little bit less used now because there's so much nickel in it. Titanium, we do have some nice titanium frames in the office. The one that comes to mind is Blackfin. So those are if you're in Sudbury, or Concord, you should check those out. They're super lightweight. They're just super strong. They can make them in such a to be very bendable. Like the temples of Blackfins are super flexible yet super strong and durable. So that's a fantastic material. It's also really hypoallergenic, so people aren't going to have trouble, skin wise or getting any kind of allergies or redness from it. Memory metal, that would be what our B-Flex ones are made from. Also the Flex-On frame, so has titanium in it, super flexible, super strong, bounces back, right? So you can kind of fold those in half and they will just come back to their shape, but they are a bit more expensive, right? You can imagine that a material that does that is going to be a bit more expensive than others. All right, aluminum, definitely not something that's super commonly used now. Nice because it's lightweight, but is not easy to be soldered, which is a very kind of common thing with metal frames. It's hard to come by a metal frame that's not soldered in some way. So has some disadvantages there. We talked a little bit about carbon fiber. Um, we do not have any gold frames, but they do definitely exist. They sometimes will be like gold that's in a temple, whether it's just kind of, gold filled. There can be solid gold frames. If you've heard of Cartier frames, they're kind of the classic ones, Cazals, that do, gold, diamonds, what have you. You can have, $10,000 frames. I will tell you, very, very popular to see Cazals and Cartiers around New York City. Definitely a market in certain demographics for that type of stuff. So I did not see them much in Massachusetts, but in New York, you do see them quite a bit, which I think is kind of funny, just kind of a different place. So last, I think we spent a little bit of time talking about some of these, the natural materials, the stone, the buffalo horn, definitely something you would see in a higher end optical shop or kind of a niche manufacturer. Kevlar, I mean, you think about it, I always think like military, army, like Kevlar vest when I think about that. So those are, if you were to get asked a question about that, it's going to have a lot of the same properties as you would expect, some kind of armor related thing to have. And then rubber, again, not super common. We did have, that reminds me of Miraflex. I don't know if you guys have seen the Miraflex, the kids frames that we used to sell more of in the offices, but honestly, those weren't rubber, those were plastic, but they had kind of some of the same properties. Like you don't have to have a hinge, they kind of bounce back. You can't really break them. So those, might be good for very durable applications. All right, I know I need to let you guys go. If you have a second, I did, or at another time, but I did, I believe, send you, let me just check here. I sent you some, it's kind of a similar thing, but it actually has some real pictures of some of these frames, which I thought were really cool to see. It's a link at the bottom of the class page that I sent you. So if you have a second later or another day, take a look at that because it's just kind of neat to see like the vintage frames in the old vintage materials. So kind of neat stuff. All right. So I will finish up a couple things we didn't get to today, but I will finish up next time. And then in the next 4 or so days, I will post stuff for the next class. If you want more examples of the base in and the base out prism stuff, definitely let me know because we can go through more of that too. We are going to return to optical cross stuff as well. So if you're not, feeling super confident in that, we are going to kind of go back to that again. All right. Thank you guys. I will let you go and have a good night.
Thank you. Have a good
Thank
night.
you.
Bye. Thank
Thank
you.
you.
Bye.
Bye, guys.
Guys.